This is Group 6's presentation for the AAE421 project. I am John Sullivan. I am joined by Christian, Thomas, Jake, Ethan, Adam, Zach, Brian, James, and Dylan. Our project consists of a lighter-than-air robotic vehicle that has its longitudinal and lateral motion controlled by two sets of propellers. Our group's goals were to develop a controller design and simulation for this blimp. I will now pass it off to Adam to talk about the open-loop system performance analysis.
Hi, I'm Adam McDivitt. Here we have listed the response parameters of all three transfer functions while they are just open loop systems. The longitudinal transfer function gives a 0% overshoot, a settling time of 235.17 seconds, and a steady state error of 5,292.1%. The rotational system gives a 99.567% overshoot, a settling time of 168,188 seconds, and a steady state error of 514.42%. Lastly, the forward system gives a 0% overshoot, settling time of 24.874 seconds, and a steady state error of 98.7%.
Hello, this is Dylan Kerr. The slide shows the three root loci representing the three dynamical systems: longitudinal, rotational, and forward mode dynamics. The root loci for the longitudinal and rotational dynamical systems show that their respective systems are stable for all gains greater than 0 because the root locus does not cross the imaginary axis and stays in the left half plane for each system. The same cannot be said for the forward mode dynamics system because the root locus is located in the right half plane for gains greater than 140. As a result, we cannot say that the system is stable for all gains greater than 0.
I'm Gene Starkey, and for longitudinal we used the PID for the closed loop system and used the control system tuner app in Simulink. We found a 2.5% overshoot and a time constant of 0.1 as the best design parameters. This outputted an overshoot of 2.54%, settling time of 0.57718, and a steady-state error of 0.11349%, with proportional gains equaling 0.8961, the integral gain equaling 0.3264, and a derivative gain equal to 2.64, with a filter coefficient of 15.51. Now for the two lateral controllers, the first step implemented was the control system tuner to obtain initial gain values. We used the tuner to get a slow rise time and poor settling time, which was not fit for our situation. This is because the tuner prioritizes a steady state error, and upon realization we changed it to metrics in the PID tuner. We prioritized the rise time because we wanted to ensure that the response would be close enough to the circle at the bottom right hand corner of the screen. For the rotation, the overshoot is 37.334%, settling time is 11.529 seconds, and a steady-state error is 0.11043%, with proportional gains of 130.47, integral gains of 0.3264, and a derivative gain of negative 111.46 with a filter coefficient of 1.145. For the forward, the overshoot is equal to 10.318%, settling time is equal to 7.81 seconds, and a steady-state error of 0.151%, with proportional gains of 230, integral gains of 50, and a derivative gain of negative 150, with a filter coefficient of 2.339.
After adding the controllers, the responses got a lot better. The overshoot for the longitudinal model was 2.5%. The settling time was 0.57 seconds, and the steady-state error was 0.13%. For the rotational model, the overshoot was 37.334%. The settling time was 11.5 seconds. The steady-state error was 0.11%. For the forward model, the overshoot was 10.3%. The settling time was 7.81 seconds. The steady-state error was 0.15%.
Hey everyone, I'm Christian. This image shows altitude control over a 5-second interval. As given to us in the problem statement, the blimp is to climb 1 meter and hold its position during tracking. To test the linearized longitudinal transfer function with the PID controller, we would input be a step response with a step occurring at 1 second and rising to a final value of 1,000 millimeters. As seen, the system quickly stabilizes at the 1 meter mark.
The next simulation task was to simulate the closed loop system output trajectory in Simulink when conducting a heading hold. In order to test the heading hold, we implemented a step input of pi radians into the linear rotational dynamics closed loop transfer function to see how quickly the blimp would turn 180 degrees. We prioritized settling time when designing the PID controller for the closed loop system, so we allowed it to have a large overshoot so the system would have a quicker response to reach the desired input. As you can see from the figure, the system overshoots the desired value before settling to a heading of pi radians around 11 seconds.
Hi everyone, I'm Thomas Wells and I'll be covering part 3 of D. So the first thing that we did was calculate the angular rate that the heading would change at in order for the blimp to complete a full revolution of the circle at a constant forward velocity of 0.3 meters per second. We did this by calculating the distance the blimp had to travel based on the circumference of the circle and divided that number by the forward velocity to determine the time needed to travel the path. We then divided 2 pi by that time to determine the angular velocity needed to travel one full revolution. This number was integrated and then inputted into the closed loop system of the rotational dynamics transfer function to determine the heading angle. This heading angle was split into sine and cosine components and multiplied by the velocity to create a vector tangent to the circle that can be represented by x and y components of the body frame. Once modeling this in Simulink, we ran the model for 167.55 seconds and outputted the x, y, and z position at every time step to the MATLAB workspace so analysis could be performed, which will be covered next by Jake.
Hello, I'm Jake Compton and I'll be analyzing the data for part D. So we ended up choosing to find the error by determining the total distance that our blimp traveled and comparing that to the total distance that it would have traveled if it followed that target drone perfectly. So as you can see on the screen, we first used this displacement formula to find the total distance that it traveled. We calculate that displacement between each point along the blimp's path and then sum those all together to get the total distance that it traveled. We then compared that to what distance it would have traveled if it followed the blimp perfectly, which is the x in that error formula there. And once we calculated that out, we got an error of 0.7609%, which is showing that overall our blimp followed that target drone very closely and our controllers worked very well.
Brian Burke here. In conclusion, the team designed a control system that consisted of 3 closed loop systems, an altitude controller, a heading controller, and a forward speed controller. We used 3 separate PID controllers tuned independently to maximize performance for 3 tasks. The tracking performance is shown in the figure here with the blimp's motion in red and the target's motion in blue. To quantify performance for the circle tracking, the error in the distance traveled compared to a perfect circle was computed. We were able to achieve an error of less than 1%.